Thanks very much, Jason, and welcome everybody who's here. It's great to see so many people having an interest in this particular field. Now, because we've got a number of visitors from outside of Queensland, I thought I'd just start by giving a little history lesson of what's happened in infectious diseases research in Queensland over the last 150 years, basically. So Yehuda and Mark, I'm not going to quiz you as to who this guy is, but this man's name was Dostoevsky, wrong. This guy was only an author of scientific papers, not of anything else. But this guy's name was Bancroft, and he was the person who first described the etiologic agent of filariasis. So 150 years ago in Queensland, filariasis and elephantiasis was endemic here. And in fact, still our dogs get a form of this that we call heartworm. And so Bancroft not only discovered the etiologic agent Wuchereria bancrofti, but he also was the first person who identified that dengue fever was transmitted by mosquitoes. So he really had an early influence on the field of tropical medicine. Now, I mentioned to Yehuda before that, in a way, Queensland has been heavily influenced by what's happening in rural areas. And there's no doubt that there are more sheep than humans in Queensland. And in the early 1940s, very close to the Brisbane airport, there was a large abattoir. And a researcher called Derek was sent by the Public Health Department to investigate a series of febrile illnesses in abattoir workers here in Brisbane. And his laboratories were literally 100 metres from here. And he determined that the etiologic agent was infective, it wasn't toxic, and he worked with Macfarlane Burnet, who was a Nobel Prize winner, to determine the cause of Q fever. So in fact, he had the first etiologic or epidemiologic description of Q fever and the actual etiologic agent. So it's caused by Coxiella burneti, and that was because of Macfarlane Burnet's contribution to it, but it was really Derek who made the first real discovery. In the mid-1990s, there was, again very close to the Brisbane airport, a racehorse trainer who became unwell and subsequently died from a multi-system illness, mainly a respiratory presentation, and 14 of his racehorses also died. And this was quite an embarrassment for public health microbiology. I think I'm safe that no one in the room was doing microbiology here in 1993, but it was the veterinary microbiologists who determined that it was a novel paramyxovirus that caused the fatal infection. That virus is now called Hendra virus because of the suburb of Brisbane where it was discovered. But from a global point of view, this virus is virtually identical to a virus called Nipah virus, NIPAH, which caused outbreaks in Singapore and Malaysia and is an ongoing problem in Bangladesh and eastern India, mainly in those areas causing a viral encephalitis that really has a very high fatality rate. So another discovery here in Brisbane. And finally, Ian Fraser, I don't know the name of the poor subject, who's looking a bit pale and not that happy. But when I was a registrar here, Ian was one of the consultant immunologists, and I thought he was just, one of the guys. But in fact, he had a very impressive research program that led to the development of the vaccine against HPV, human papillomavirus. And so I guess we're all expecting a Nobel Prize to come to him at some stage, because it was really his work that directly led to that. And I think that ended up becoming a Merck product. I'm not sure. I know yes, it is. Okay. I don't know if it still is patented, but obviously that's been, already there are studies in Australia showing the reduction in cervical cancer. So that's just a little bit of background. I want to now move to the real topic, sorry Jason, and talk a little bit about the epidemiology of resistance in gram-negatives in Australia and in the Asia-Pacific area, because it is quite different from what you might read about in work coming from the United States or even Israel or the United Kingdom, although I guess the UK is probably having a little bit of similarities. And then how do we tie that into surveillance and antibiograms and come down to antibiotic selection for our individual patients? Now, I know that Mark's talking about staph and C. diff, maybe enterococcus, I'm not sure, so I'm not going to cover gram-positives at all. So one of the real barriers to understanding molecular epidemiology of gram-negatives is that the classification scheme is so ridiculous. And unfortunately, there are multiple classification schemes. There are all these three-letter abbreviations which have no consistency. And so, for example, TEM, which is a common beta-lactamase, is named after Mrs. Temonira, who was a lady in Athens in 1964 who got an E. coli urinary tract infection. I don't think we'd be letting our patients' names out quite as widely these days with all our privacy laws. So there's that extreme, and then, CTX-M. The CTX means cefotaximase. The M is for München, for Munich, which was where the beta-lactamase was first discovered. So completely ridiculous. And then there's different abbreviations that sometimes mean exactly the same thing. So the simplest, if you can call it this, is one that just goes A, B, C, D. And A are your very common simple beta-lactamases that knock out ampicillin in E. coli. And then modifications of those are the ESBLs, and they're called extended spectrum beta-lactamases because instead of those simple knocking out of ampicillin, an amino acid change means that the active site is widened and can now destroy third-generation cephalosporins. And they're our ESBLs. And so some of them are modifications of TEM and SHV. The most common one now worldwide is the CTXM type. And then KPC, which is actually a carbapenemase, is also one of these class A enzymes. Class B are the metallobeta-lactamases, and I'll talk about those in some detail. These are carbapenemases, so they wipe out meropenem. Class C is your AMP-C beta-lactamases, and so we've all been taught that, if you're treating Enterobacter, you're not going to use ceftriaxone or ceftazidime, even though it might look susceptible occasionally from the lab, and the reason being that these have an intrinsic beta-lactamase that destroys third-generation cephalosporins. And finally, Class D are the oxa beta-lactamases, which if you read Acinetobacter literature, and I'm going to talk a little bit today about Klebsiella and E. coli literature, they're a fairly diverse group of beta-lactamases. Some are like ESBL, some are like carbapenemases, and some are even different from that. So that's sort of the framework. So today I want to talk a little bit about the epidemiology of carbapenemases. And so Class A representative is KPC. Class B are the variety of metallobeta-lactamases, and Class D, the oxa type. So let's go through those in turn. Now this is a pretty ancient map, but the epicenter of KPC was really New York City and subsequently the northeast of the United States, and closely behind was Israel. But now in every continent we've got KPCs. Australia has been largely spared. There have been some outbreaks luckily in other cities other than ours, but it is really fairly lower, substantially lower down in the list of importance in Australia and also Southeast Asia than it is in the United States and Western Europe. but it does still crop up in China, other parts of Southeast Asia, so we certainly can't rule it out as a possibility. And probably the biggest group of patients who we see with KPC producers are actually people from Italy or Greece. So Yehuda, you haven't met that many drunken Australians yet, but a typical thing would be to go on a drunken holiday in Rome or the Greek islands, end up in a hospital, get repatriated back to Australia, and they're the sort of people who will often have KPC producers. Now, OXA48 is one a lot of people haven't heard about, but even in Brisbane we've had outbreaks, pretty large outbreaks, of OXA48 and its relatives. And Turkey was probably the originator of OXA48, or certainly where the first descriptions were, and then in northern Africa, but it has subsequently spread quite nicely to Europe and is a substantial problem in places like Spain and France and occasionally in the United Kingdom. And a variant has been quite well described in India. So these are sometimes low-level carbapenemases, in that clinical microbiology laboratories may have difficulty in actually saying that this is a meropenem-resistant isolate that does have clinical significance. And there was a famous court case in the Netherlands where 2 microbiologists were actually sued by the country for their failure to detect OXA48, and subsequently there was an outbreak of OXA producers, which really would be egg on the faces. I thought the poor things, they didn't deserve, it was pretty subtle detecting some of these enzymes, but they got dragged along, and everyone knows their, well, I'm sure everyone in Holland knows their names. So OXA48, yes, we certainly have had them in Brisbane, we've had them in Australia, and we have them in Southeast Asia. And then NDM, which some people call the New Delhi metallo-beta-lactamase. I guess many people in India suspect that it actually originated in Pakistan. We're not 100% sure, but there's all sorts of political tensions. And this is certainly has become a big issue throughout Southeast Asia. It's, just to re-emphasise, it's one of the metallo-beta-lactamases, and that creates problems in terms of its treatment. So it hydrolyses or destroys penicillins, cephalosporins, carbapenems, but interestingly not as trienam, and that may have some potential treatment efficacy. It's not inhibited by clavulanic acid or tazobactam, so piptaz or other tazobactam or clavulanic acid combinations aren't going to be effective, frequently resistant to ciprofloxacin and Bactrim, and frequently goes hand in hand with the 16S ribosomal RNA methylases, which lead to high-level resistance to aminoglycosides. So when we get an NDM producer, we're in pretty tough sort of territory. There's been a whole variety of them, often in Klebsiella, but also E. coli and Enterobacter, and they are typically plasmid mediated. So why has this become such a big issue in India and Southeast Asia, and why is it something we're concerned about here? Well, this is an example. I don't know if in the United Kingdom, do you have Where's Wally, Mark? Yes. So it's a bit like Where's Wally. If you find the W, that's where drinking water in New Delhi was contaminated by NDM-producing bacteria. So you can see why it's become a huge problem, because in the wet season, the rainy season, it's going to contaminate drinking water. And there's also been publications from China where it's in organisms of food animal origin. So basically, people in India and other parts of the world are eating and drinking NDM-producing organisms. This is a slide that was produced for a different reason. This is from China, and it was looking at healthy people who the proportion that were colonised over time with ESBL producers, and you can see it's sort of 70 to 80 to 90%. And it's not going to be surprising if in India and other parts of Asia, we're going to have large proportions of the healthy population now colonised with carbapenemase producing organisms. So in Australia, we see it predominantly imported from the Indian subcontinent, but not exclusively from India. I've had a number of patients from Myanmar, and we know that it exists in Singapore and Thailand. And there have been some examples of local acquisition in Australian hospitals without overseas travel, but we don't have it endemic in any institution. What is endemic in Australia is a metallo-beta-lactamase called IMP4, which is not common elsewhere in the world. This is a fairly old slide from isolates from here in Queensland that were Enterobacter that were resistant to carbapenems, and you can see quite a smattering of them were IMP4 producers, and we've found that it can be very recalcitrant in terms of being stuck in hospitals, and Patrick might or might not talk about molecular epidemiology of IMP4 in local hospitals, in which, to our surprise, IMP4 producing strains have been stuck in our ICU environment, unsuspected for many years. So how are we going to put all this together? So one importance of surveillance for these types of carbapenemases and resistance in gram-negatives is really to improve our infection control. And so certainly our hospitals will have guidelines where we would preemptively put people into contact isolation if they've been hospitalised recently in high-risk countries. And that can, knowledge of the fact that we've got an NDM producer or an OXA producer can allow sort of more wide-scale local surveillance for infection control purposes. But how about from a clinical perspective? Well, if we've got a carbapenem-resistant organism, our traditional choices have really been to go to colistin or tigecycline. Unfortunately, intravenous fosfomycin is not marketed in Australia, but people can get hold of it. We've got ceftolozane tazobactam, which may be effective against carbapenem-resistant Pseudomonas, and possibly some of the OXA beta-lactamases. Ceftazidime avibactam is not yet available in Australia, and perhaps Yehuda might mention of its potential combination with aztreonam. So the trouble is, for all of these treatment options, there are problems. For colistin, I haven't gone into the emerging resistance mechanisms, but they are now numerous. And tigecycline and fosfomycin, and as well as the newer drugs, there are all particular resistance mechanisms. So from my point of view, to boil all that down into some principles of antibiotic use, for community onset infections, if we're treating them here in Australia, we've got to consider whether there is a risk for an ESBL producer. And certainly residence in Southeast Asia is a substantial risk factor, and there are a variety of other risk factors such as being in a nursing home or even being of Indian origin without recent travel is potentially a risk factor for ESBL producers. And meropenem would be the preferred agent, but there are certainly investigations going on over carbapenem-sparing options, such as, for example, ceftolozane tazobactam or piperacillin tazobactam. For hospital-acquired infections, I think in general we would be guided more by unit-based surveillance. In other words, what's going on in a local ICU or in a haematology ward, then really an Australia-wide or a region-wide antibiogram. And certainly if we know individual patient data, for example, that this person has been colonised with CRE or a carbapenem-resistant Pseudomonas, and they've come to ICU with sepsis, or they're in a haematology ward and they're neutropenic. I think in that situation we could justify empiric therapy against carbapenem-resistant Enterobacteriaceae or carbapenem-resistant Pseudomonas, if that's what we know they're colonised with. But what we don't really know is if in our units we've got a certain level of resistance, say more than 10% of our Klebs and Enterobacter are resistant to meropenem, should we then be routinely using anti-CRE or anti-carbapenem-resistant Pseudomonas antibiotics on an empiric basis? And I think that's something worthy of a trial, or certainly of debate. So finally, for us here in Australia at the moment, when we're talking about gram-negatives, it's all about carbapenemases and colistin resistance mechanisms. That's what's getting us excited. But I think very soon, colistin is going to be a thing of the past. And carbapenems aren't going to be a thing of the past, but they're still going to be, we're going to have a lot more focus on the new drugs that Yehuda is going to be talking about, and how do we predict or even detect in the laboratory resistance to those agents. And clearly, surveillance and antibiograms are going to be much more sophisticated in the very close future, in that we're going to be using whole genome sequencing as part of our surveillance. We're hopefully going to have genome predicting phenotype and using that in our antibiotic selection. So even pharmacists and certainly microbiologists will have to get savvy about the detection of genes, because what is the implication going to be then on treatment? And we're going to be using temporospatial mapping of our resistance genes in our hospitals to try to determine who is at risk and what we should be doing for infection control purposes. So I'll finish there, and will we take questions now? Yep, thank you.